Hi everyone, I'm Victor Besnier, and I'm happy to present to you our work entitled Triggering Failures Out of Distribution Detection by Learning from Local Adversarial Attack in Semantic Segmentation. Nowadays, deep neural networks have shown very promising results for vision tasks on academic datasets like Cityscape, ImageNet, or MS-COCO. But when we want to export our model outside of the labs, we are not only looking for accuracy on known classes, we also want our model to be reliable on their predictions, as error could cost lives in case of safety-critical application. For automated vehicles, an OOD example will induce a wrong prediction, resulting in a wrong behavior of the system and could lead to a car crash. So how to prevent failure of the system? To answer this question, we present a novel framework dedicated to OOD and error detection, named Observer Network. The idea is straightforward. Let's say that we already have a pre-trained target network here for semantic segmentation. This network is used only for class prediction and is frozen for the next step. The observer, meanwhile, is an additional network connected to the target network. The observer takes as input the image and also internal activation of the target network, which allows it to observe the process of the decision made by the target network. OBSNET mimics the architecture of the segmentation model. This auxiliary network is dedicated to anomalize and error detection. It is trained on the failure of the target network and thus outputs an uncertainty map. Finally, the observer runs in parallel with the target network. The frameworks allow to have both the segmentation and the uncertainty. The performance of the target network is preserved as it is used off the shelf and is frozen during observer training. But the training of the observer raises two major challenges. First, as it is trained on the error made by the target network, the training will be very difficult due to potential overfitting on the training data. Secondly, the observer will only see in-distribution sample, which could be harmful when facing a OOD sample at test time. To address both of these problems, we propose a custom type of adversarial attacks. We add a local perturbation in a random localization and a random shape to trigger failure of the target network. Thanks to it, we are able to hallucinate new instance mimicking an OOD for which we do not have any prior information about the appearance and shape. Local adversarial attack has the following properties. It is a proxy to detect OOD. It increases the amount of available errors to train the observer. And compared to methods that perform adversarial attack at test time, we only use it during training, thus preserving the inference time during test. The inference is not changed. We simply make forward passes through both networks. I will now present the results. We evaluate our method on three different datasets, 4 metrics of error detection and calibration, and against numerous methods. We show that our method is both accurate and calibrated. Visually, our method shows stronger response on OOD sample and can also highlight regular error regions, such as class boundaries. Finally, our framework has several advantages compared to others. It is more accurate on OOD and error detection, it is faster, and it is memory efficient. To conclude, we propose a new framework called Observer Network dedicated to OOD and error detection. We aimed at mitigating the most common pitfall by covering two main aspects. The architecture, we use a dedicated network for OOD detection and a residual connection to observe the entire network, and the training, by generating data that unravel blind spots of the target network thanks to local adversarial attack. Finally, we show that our method is fast, accurate, and have a light memory footprint. You can download our code by following the link